Okay, let's unpack this. How often do we, as senior software engineers, find ourselves staring down a complex, elusive bug, you know, tirelessly tracing lines of code, meticulously examining logs, only to realize the real problem isn't like in a faulty algorithm or a missing semicolon?
Right. Or even a misconfigured dependency.
Exactly. The root cause is far deeper, isn't it? It's often embedded in the very architecture of the system itself, or maybe even in how our teams are, well, structured and interact.
Hmm. It's like trying to fix a leaky faucet by just tightening one pipe, when the issue is actually the whole building's plumbing design.
Yeah, precisely. And what's really fascinating, and I think often overlooked, is that software systems, in all their complexity, they behave a lot like natural systems. They seem to be governed by these fundamental principles that shape how they work, how robust they are, how they evolve.
Precisely. And that's exactly why today's deep dive is into Chapter 3, Why Systems Work So Well, from Donella Meadows' a really foundational book, Thinking in Systems, a primer. Absolutely. So our mission today is to go beyond just the surface definitions. We want to extract the critical insights about three really key system properties: resilience, self-organization, and hierarchy.
Okay.
And we're not just defining them academically, we're going to translate these deep understandings into actionable, practical knowledge specifically for you, a senior software engineer working on complex systems day in, day out.
Right.
Because Meadows argues very clearly that really understanding how systems inherently work well, how they maintain themselves, adapt, evolve, that understanding is crucial before we even try to fix them or change them.
Otherwise, our fixes can backfire, right?
Exactly. Without that fundamental systemic view, our best intentions can sometimes lead to unintended consequences, maybe even create more problems down the line.
And why does this distinction matter for you, our listener, like right now in your daily work? Because these aren't just abstract theories for a coffee break chat. They are, I think, powerful lenses. Practical ways to view, design, and importantly, troubleshoot the robust, adaptive, maintainable software architectures we all strive for. We'll explore how these principles show up directly in the choices we make every day. From big architectural decisions like monoliths versus microservices to the dynamics within our agile teams.
And even how the organization itself is structured?
Yes. And maybe more importantly, we'll look at how ignoring these deep systemic principles can lead to, well, pervasive technical debt that just cripples future work, endless operational fires, and even that team friction that just grinds everyone down.
Yeah, absolutely. So ultimately, this deep dive is about giving you the framework to build systems that don't just work today, but systems that can truly adapt, evolve, and, thrive in the future, whatever that unpredictable future holds.
Yeah.
Hashtag the power of resilience in software systems.
Okay, so let's start with resilience. It's probably one of the most critical properties for any robust system, especially in software. Meadows gives us a very clear, almost intuitive definition.
Oh, okay.
She says it's the ability to bounce or spring back into shape, position, etc., after being pressed or stretched. Elasticity.
Elasticity, okay.
Yeah, and the key thing to grasp here is that true resilience isn't about a system being static or rigid. It's not about never changing when stressed.
Right. It's not brittle.
Exactly. It's about its dynamic capacity to endure perturbations, absorb shocks, unexpected traffic spikes, network failures, security issues, and then restore its core function, even if that means changing temporarily or, say, shedding non-essential features for a bit.
Like a spring you mentioned. It bends but doesn't break, comes back to shape. Precisely. It moves, compresses, expands, maybe even deforms slightly, but it returns to its original form, or at least a functional state.
Yeah.
And what's really fascinating is how Meadows says this resilience happens.
Okay.
She knows it comes from multiple mechanisms at different timescales, and with redundancy, one kicking in if another one fails. So it's not just one wall of defense. It's layered, diverse.
Multiple levels.
Yes, and she even talks about higher levels, like meta-resilience. That's feedback loops that can rebuild other feedback loops, and even meta-resilience loops that can learn, create, design, and evolve entirely new ways to recover.
Okay, wow. Meta-resilience. That really hits home for software, doesn't it?
How so?
Well, think about automated rollback systems or infrastructure as code deployments. If a bad deployment goes out, right, you're monitoring that's a feedback loop detects an issue. Then your automated deployment pipeline, another feedback loop, triggers an immediate rollback to the last good version.
Right, one loop triggering another to restore state.
Exactly. Or Kubernetes self-healing. A pod fails, the controller sees it, spins up a new one. It rebuilds that feedback loop of the running service automatically.
That's a great example of meta-resilience. and meta-meta.
That feels like maybe the blameless post-mortem process, where you don't just fix the bug, but the incident data and the deep dive analysis lead the teams to actually redesign the deployment pipeline itself.
Ah, yes. Learning and evolving the structure.
Yeah. Maybe they implement canary deployments or better feature flags. The organization learns from the failure, evolves its processes, and designs new structures to stop whole classes of failures. It's moving beyond just reacting.
That's the depth. Exactly. That's a system truly evolving its own resilience. But Meadows warns us, and this is crucial for us, because resilience may not be obvious without a whole system view. People often sacrifice resilience for stability, or for productivity, or for some other more immediately recognizable system property.
Oh, the classic trade-off. The pressure to ship features fast versus building something robust.
It's that constant painful tension. And it's a trade-off often made implicitly, without fully understanding the long-term systemic cost.
Absolutely. And if we connect this to, say, the shift from monoliths to microservices, Meadows' point becomes crystal clear.
How do you see that?
Well, a monolith, right. It might seem stable because it's one deployable unit, maybe easier to reason about initially in a narrow scope, but it's often incredibly brittle under real stress. Like if one component inside, say, a complex reporting module has a memory leak, it can just consume all the resources and crash the entire application. Everyone's down.
Lacking that redundancy Meadows talks about. A single point of failure.
Exactly. It doesn't have those multiple mechanisms she described.
Right. Contrast that with microservices architectures. Here, the explicit goal is often resilience, fault tolerance, graceful degradation. It's designed to combat that monolith brittleness.
Okay.
Services are isolated. They talk through defined APIs, maybe async messaging. So failures in one service can ideally be contained.
So if the user auth service fails...
Right. Maybe your e-commerce site still lets people browse products, add to cart, maybe even check out if they're already logged in, or you allow guest checkout. They just can't log in or finalize certain actions until auth is back.
So part of the system still works. It degrades gracefully.
Precisely. A single service failure doesn't necessarily kill the whole experience. Other services keep running or offer reduced functionality. That directly mirrors Meadows' point about multiple mechanisms and redundancy. Each service is like an independent mechanism.
Okay, that makes sense. And this brings us back to that Meadows warning. How often do we sacrifice this resilience for what looks like productivity?
Yeah, the technical debt connection.
Exactly. Meadows' observation about sacrificing resilience for productivity or immediately recognizable properties, that maps directly onto technical debt, doesn't it?
I think so. Explain.
Think about those quick fixes under deadline pressure, the whole ship it now, fix it later thing. Maybe we neglect proper error handling for some third-party API call.
Or skip writing comprehensive logs because it might impact performance slightly.
Right. Or weak retry mechanisms. Or just ignoring those edge cases because they probably won't happen.
Seems productive short term. Faster feature delivery. Looks like high velocity.
But then the loan comes due, as you said earlier.
Is it always? That initial productivity gain, it's really just borrowing from the future, introducing fragility.
Brittleness.
Exactly.
Yeah.
So the next unexpected load spike or that API returning a weird error or just a shift in user behavior, suddenly those shortcuts break things. The system is less resilient.
And it's not just one bug. It piles up. It becomes technical debt.
Which then slows down future development because changes are harder, increases operational costs, I think late-night pages, emergency fixes.
Engineer burnout, team morale takes a hit from constant firefighting.
Yeah. It's a classic case of optimizing locally, that quick feature delivery, but at the expense of the whole system's long-term health and adaptability. Meadows shows us these aren't just coding mistakes. They're systemic outcomes of, perhaps, misaligned incentives.
So, given that resilience can be hard to see until it breaks, Meadows says resilience is something that may be very hard to see unless you exceed its limits and the system structure breaks down. Which begs the question, right? How do you know if your system is resilient before it fails catastrophically in production?
That's the million-dollar question. How do you test that elasticity proactively?
Right, without waiting for a real disaster.
Well, that's exactly where something like chaos engineering fits in. It's a direct, practical application of this systems thinking principle.
Okay, explain chaos engineering through that lens.
It's the practice of intentionally injecting failures, perturbations, as Meadows might say, into your distributed system, but in a controlled way.
In a safe environment, hopefully.
Ideally, yes. Or very carefully in production. You're deliberately pushing the system to exceed its limits. Maybe introducing network latency between services or shutting down instances of a critical dependency, spiking CPU.
Even messing with data stores.
Potentially, yes, in controlled experiments. The goal isn't just to break things randomly, is to understand the system's true elasticity and, critically, to verify that your safety nets, your monitoring, your alerting, your failovers, your automated recovery mechanisms actually work as you expect them to.
So you're building that muscle for recovery, finding weaknesses before users do.
Exactly. You build confidence in the system's ability to handle turbulence. It transforms incident response from just reactive firefighting into a continuous cycle of learning and improvement. That's fostering that meta resilience we talked about, designing for failure, building systemic confidence through deliberate stress. Hashtag, tag, the dynamics of self-organization. Okay, let's move to our second deep property, self-organization. Meadows describes this as the most marvelous characteristic of some complex systems, their ability to learn, diversify, complexify, evolve.
Learn, diversify, complexify, evolve. Wow.
Yeah, it's the capacity of a system to make its own structure more complex. Think about how a single fertilized egg cell develops into a, incredibly complex human being.
Or how life itself branched out into millions of species from simple beginnings.
Exactly. That's self-organization. It's not a top-down blueprint imposed from outside. It's emergent complexity arising from within the system itself. It creates its own order, often in surprising ways.
What's fascinating, though, and maybe a bit scary for traditional management, is what Meadows says it requires.
Which is?
She highlights that self-organization requires freedom and experimentation and a certain amount of disorder.
Disorder. That's the word that often makes people nervous.
Right. She notes it can be scary for individuals and threatening to power structures because it leads to heterogeneity and unpredictability. It means letting go of some direct control.
Which feels counterintuitive if you believe control equals order. But Meadows suggests that's actually where the real innovation and adaptation happens, in that space of managed disorder.
But it's not total chaos, is it?
No, not at all. And that's the crucial part. Meadows emphasizes that just a few simple organizing principles can lead to wildly diverse self-organizing structures.
Simple rules, complex results.
Exactly. Think of a Coca snowflake fractal. Beautifully complex, infinitely detailed, but generated by applying one simple geometric rule over and over.
Or DNA. A few basic chemical rules leading to the incredible diversity of life.
Precisely. Meadows says out of simple rules of self-organization can grow enormous, diversifying crystals of technology, physical structures, organizations, and cultures. The universe itself seems to work this way. The key isn't dictating the final outcome, but defining the foundational rules that allow the outcome to emerge.
Okay, let's translate this directly into software engineering. How does this apply to us, senior engineers dealing with teams and processes?
Well, Agile and Scrum methodologies are, I think, perfect examples of self-organization in practice.
How so?
Teams are given a goal, like a product backlog, features to deliver, and then a set of simple rules to operate within.
Like daily stand-ups, sprint reviews, retrospectives.
Definition of done, time-box sprints, yeah. These aren't step-by-step instructions on how to write the code. They're a framework for how the team collaborates, communicates, adapts.
They set the boundaries, not the exact path inside those boundaries.
Exactly. And within those rules, teams are empowered to self-manage their work. They decide how to achieve the sprint goal, how to tackle problems, how to adapt to changes, all without constant detailed direction from above.
Right. They learn in retrospectives, maybe diversify skills as people pick up different tasks.
And they complexify their solutions based on feedback from product owners, users, other teams. Innovation bubbles up from the people closest to the problem.
That's the engine for continuous improvement, right? The team itself becomes a learning system.
It fosters real ownership, too. And this scales up, right? It's not just small teams.
Oh, yeah. This is where it gets really profound, I think. Consider something huge like the Linux kernel ecosystem, or maybe the whole Node.js community.
Monumental examples of large-scale self-organization.
There's no CEO of Linux dictating every feature, right?
Right.
No central planning committee for node modules. Yet they work, they evolve, they power so much of the world.
Exactly. You have millions of developers globally contributing, often asynchronously, across cultures and time zones. What holds it all together? How does it maintain quality and coherence?
The simple rules.
Precisely. It's adherence to a set of shared simple rules, the project's organizational DNA. Things like common communication protocols, strict coding standards, rigorous merit-based review process for patches.
Where code gets accepted or rejected based on technical merit and following the guidelines.
Right. And clear communication channels like mailing lists or forums. These aren't rigid top-down commands, but a shared understanding of how to contribute effectively.
So you have that experimentation and disorder from individual contribution.
Balanced by the structure of peer review and acceptance by trusted maintainers. It perfectly mirrors Meadows' insights. It's decentralized, seemingly chaotic, yet produces incredibly stable, complex, evolving software.
Adapting constantly to new hardware, new needs through this collective emergent intelligence.
Oh, yeah. Hashtag the double-edged sword of hierarchy. Okay, third property, hierarchy. Now, Meadows argues this isn't just some arbitrary corporate structure. It's actually a natural, often necessary outcome of self-organization itself. It's how systems manage growing complexity.
So complexity leads to hierarchy.
In a way, yes. She says complex systems can evolve from simple systems only if there are stable intermediate forms. The resulting complex forms will naturally be hierarchic.
Stable intermediate forms, like in biology.
Exactly. Cells form tissues, tissues form organs, organs form systems like the circulatory system, and those systems make up the whole organism. Each level, tissue, organ, system is a stable intermediate form. It allows complexity to build without overwhelming any single part. Hierarchy is the system's strategy for dealing with its own complexity.
And hierarchy does offer real benefits, right? Especially in software systems.
Absolutely. It provides stability. It reduces the information load on higher levels. A team lead doesn't need to track every single line of code.
Just like a CEO doesn't need to know the details of every team's stand-up.
Right. It allows for specialization, different components or teams focusing on specific functions, like organs in a body. And it helps manage interactions between these subsystems, preventing total spaghetti code or organizational chaos.
Meadows emphasizes keeping things aligned, right? Keeping sub-purposes and overall system purposes in harmony is an essential function of successful systems.
That harmony is key. Where the local goals genuinely serve the larger purpose, that's hierarchy working well.
And in software architecture, we use hierarchy constantly.
All the time. Modules within components, components forming services, services making up a whole distributed system.
Microservices, again, each service is like a subsystem with its own internal hierarchy, and then they interact within a larger system structure.
Yeah. That decomposition helps us manage the massive complexity of modern software. We break it down into manageable, specialized units.
There's always a but, isn't there? Here comes the trap.
The double-edged sword part.
Yeah.
Meadows warns about sub-optimization.
Ah, yes. Sub-optimization. That sounds familiar.
She says, when a subsystem's goals dominate at the expense of the total system's goals, the resulting behavior is called sub-optimization. And this is maybe one of the most insidious and common pitfalls we face as senior engineers.
Because it often looks like good engineering locally.
Exactly. Let's take a really sharp practical example, something most of us have probably seen.
Okay, lay it on us.
Imagine a team responsible for just one microservice in a big e-commerce platform. Let's say it's the product catalog service.
Got it.
Now, this team gets really focused on an internal KPI, maybe database query latency for their service. They decide to optimize the hell out of it, maybe get query times down to microseconds.
Sounds great for the catalog service.
Locally, yes. Maybe they achieve this by adopting some niche, super specialized graph database or some cutting-edge framework that's perfect for that specific task. They hit their metrics, looks like a huge win for the team.
Okay, I see where this is going.
But this local optimization might create a massive burden for the broader system. Well, maybe that niche database requires specialized operational knowledge. The central SRE team can't easily monitor it or handle incidents using their standard tools. It makes cross-service queries a nightmare for other teams using standard relational databases.
Creates data silos, inconsistent operational patterns.
Exactly. It hinders overall observability, maybe even security, if it doesn't fit standard protocols. So, the catalog team's local success becomes a global burden. That's sub-optimization. The subsystem's goal hurt the total system's effectiveness.
Which raises that huge question we always grapple with in large organizations. How do we balance the need for structure and consistency, which hierarchy gives us, with the need for speed, innovation, team autonomy, which self-organization needs?
It's the constant tug of war. Absolutely. Push and pull between top-down governance and bottom-up creativity.
So how do we navigate that using Meadows' ideas?
Well, let's look at the extremes through her lens. First, too much central control. Think of a really prescriptive architecture review board, an ARB, dictating every specific technology, framework, even down to low-level patterns for all teams.
The architecture police?
Kind of.
Yeah.
Meadows uses that powerful biological analogy. If the brain controlled each cell so tightly that the cell could not perform its self-maintenance functions, the whole organism could die.
Wow.
In software, this hypercentralization, even if it aims for consistency, often creates huge delays. Teams wait weeks for ARB approval on small things, kills momentum.
Right. And it stifles that self-organization we just talked about. Teams can't experiment or pick the best tool for their job.
Exactly. It reduces ownership, intrinsic responsibility, as Meadows might say. Why own it if the decision was made for you? And worse, it can lead to rule beating.
Rule beating.
Yeah, teams finding clever workarounds to avoid the restrictive policies, creating hidden complexities, shadow IT, technical debt that's even harder to track because it's off the books.
Right.
The system becomes rigid slow.
Okay, so that's one extreme. What about the other? Unchecked team autonomy.
Right. Empowering teams is crucial, but complete autonomy with no guiding hierarchy. That can lead to chaos, too. Fragmented, inconsistent, maybe unmanageable systems.
How's
Each team might suboptimize, purely for its own convenience. You get duplicated effort, multiple teams building their own auth systems, choosing different message queues, implementing different security approaches.
leading to incompatible services, operational silos?
An operational nightmare, yeah. Hard to operate, secure, debug, evolve. Becomes a collection of locally optimized islands that don't form a coherent continent.
So we need that harmony again.
Exactly. Finding the balance. Meadows points to that essential function of successful systems, reconciling sub-purposes with overall system purposes.
Okay, so practically, what does that look like in a software org?
It means defining clear, high-level architectural principles and goals, the purpose of the hierarchy, but making them guiding guardrails, not rigid prescriptions.
So principles over specific implementations.
Often, yes. Focus on consistency for critical things, security, observability, fundamental tech choices, how services interact maybe. But within those boundaries, you absolutely need to give teams the freedom and experimentation for self-organization. Let them choose the best tools and approaches for their problem space.
Setting the right rules at the right level.
Precisely. A central group might define the standard for service interfaces, maybe API contracts, but the individual service teams decide the internal implementation details. That way, local optimizations can actually contribute to the broader goals rather than detract from them. You get a system that's both robust and adaptive. Hashtag outro.
Okay, so pulling this all together, what does this really mean for us, the architects, the senior engineers building these complex systems? Meadows gives us these powerful lenses, right? First, resilience. It's not just stability. It's that dynamic ability to recover, adapt, maybe even transform when things go wrong, and sacrificing it for short-term productivity. That's often how we get buried in technical debt. Real resilience needs diversity, redundancy, self-healing.
Right. Second, self-organization. Enabled by simple rules and freedom, it's the engine of innovation and evolution. We see it in agile teams adapting on the fly, and in huge open-source projects evolving complex order from the bottom up.
And finally, hierarchy. It's a natural tool for managing complexity, allowing specialization. But we have to watch out for those traps, sub-optimization, where local wins hurt the whole, and finding that tricky balance between central guidance and team autonomy. Aligning those local and global goals is the constant challenge.
Exactly. Meadows really pushes us to look beyond just the surface events, the symptoms, and see the underlying structures, the feedback loops that produce those outcomes. So take these ideas and let them provoke some deeper thinking about your own work.
Yeah, maybe some reflection questions.
Definitely. Let's pose a few for you, the listener, to chew on. 1. Think about a recent significant system incident or outage you dealt with. How did your architecture, monolith, microservices, hybrid, whatever, actually demonstrate resilience? Or, conversely, where did it show its brittleness? Can you trace the feedback loops or the missing ones that affected recovery?
Good one.
2. Now consider a really successful feature development. How did the simple rules of your team's process, maybe agile rituals, DevOps practices, coding standards, enable self-organization? Did any unexpected complexities or innovations emerge from that freedom? How were they handled?
Okay.
3. Are there signs, subtle or maybe not so subtle, of sub-optimization happening right now in your projects or teams, like a specific team's tech choice or a microservice optimization that might actually be making things harder for the overall product or other teams in the long run? What are the hidden costs?
That's a tough one to admit sometimes.
It can be. 4. How does your organization currently balance central architectural guidance? Maybe an ARB, maybe principal engineers with the autonomy teams need to innovate, Where have you seen too much control stifle things or too little guidance lead to fragmentation? Where could that balance be improved?
Always a balancing act.
And finally, 5. Meadows talks about sacrificing resilience for productivity. Can you pinpoint a specific instance, maybe right now, where that trade-off is being made, explicitly or implicitly? Rushed delivery, deferred maintenance. What are the potential long-term systemic costs or benefits? Is it really sustainable?
Wow. Those are definitely deep dive questions. They're not just theoretical, right? They're invitations to see your daily work, your systems, your teams through this systems lens.
Exactly.
The more deeply you understand these underlying principles, the more effective you become as an engineer, as a leader, as a problem solver. And remember, Donella Meadows reminds us these ideas aren't just about software. They apply everywhere, organizations, economies, even our daily lives.
They're universal patterns.
So keep exploring systems thinking, engage with these questions, and remember her words. The more ways of seeing, the better.